The subcommittees on space and environment will come to order. Without objection, the chair is authorized to declare recesses of the subcommittee at any time. And welcome to today's hearing entitled Exploring Commercial Opportunities to Maximize Earth Science Investments. I'll recognize myself for 5 minutes for an opening statement. Good morning. I would like to welcome everyone to our hearing today, and I want to thank our witnesses for taking the time to appear before our committee. Today's hearing will explore opportunities for NASA to acquire Earth observation data through public-private partnerships, including commercial capabilities. NASA's Earth Science is the largest and fastest growing of all Science Mission Directorate programs. In the last 8 years, the Earth Science Division funding has increased by more than 63%. One reason for these budgetary increases is that NASA's Earth Science portfolio has expanded to include new responsibilities for the continuation of measurements that were formerly assigned to other agencies, including data continuity and application-focused satellite observation programs. For example, the President's fiscal year 16 budget request redefines NASA and NOAA Earth-observing satellite responsibilities. Under the new framework, NOAA is responsible only for satellite missions that contribute directly to NOAA's ability to issue weather and space weather forecasts, while NASA is responsible for all other non-defense Earth-observing satellite missions. The near-term impact of this revised framework includes the transfer of responsibility for TSIS-1, the Total and Spectral Solar Irradiance Sensor, Ozone Mapping and Profile Suite, OMPS, and JPSS-2 Radiation Budget Instrument, or RBI, and future ocean altimetry missions to NASA. Another example of increased NASA responsibilities is the Sustainable Land Imaging, or SLI, program. In the past, both USGS and NOAA have been responsible for development and operation of Landsat satellites. But now, NASA is responsible for 3 mission and development activities, including initiation of Landsat 9, along with a 4th activity to design and build a full capability Landsat 10 satellite. Given our constrained budget environment and NASA's new responsibilities, public-private partnerships may offer an opportunity to lower costs and improve Earth observation data while fulfilling science community requirements, including data continuity. Over the past decade, the United States private space-based remote sensing sector has made significant improvements in technology, products, and services. Leveraging commercial off-the-shelf technology, borrowing ideas from the information technology community, and developing innovative low-cost solutions with high-performance outcomes, the private sector is demonstrating new capabilities that could be used to address many of NASA's Earth observation data needs. In the past, Earth observations were associated almost exclusively with government-managed or government-sponsored projects. Today, commercial sources of Earth information are rapidly increasing in availability and scope. Commercial satellite systems are now reliable sources of high-resolution Earth imagery, and commercial remote sensing companies have greatly expanded their offerings. Technology is also rapidly changing. For certain types of missions, solutions can be built that are much smaller in size, much lower in weight, require much less power, and offer even greater data collection capabilities. It costs much, much lower than the current systems. U.S. law and national policy directs NASA to advance the commercial space sector. Pursuant to the National Aeronautics and Space Act, NASA shall seek and encourage to the maximum extent possible the fullest commercial use of space. NASA is also directed to the extent possible and while satisfying the scientific or educational requirements of the administration and where appropriate of other federal agencies and scientific researchers, acquire where cost-effective, space-based and airborne Earth remote sensing data, services, distribution, and applications from a commercial provider. A principle of the administration's States' national space policy is that the United States is committed to encouraging and facilitating the growth of a U.S. commercial space sector that supports U.S. needs, is globally competitive, and advances U.S. leadership in the generation of new markets and innovation-driven entrepreneurship. Both the 2014 National Plan for Civil Earth Observations and the 2015 National Space Weather Action Plan, as proposed by the administration, direct federal agencies to identify and pursue commercial solutions. Given the great potential for public-private partnerships, NASA is unfortunately doing very little. NASA's Earth Observation Program is the largest U.S. government civil remote sensing effort and perhaps the largest civil remote sensing effort in the world. NASA currently operates 26 Earth observation satellites with 12 under development. However, none of NASA's Earth observation satellites, either in operation or under development, are public-private partnerships. NASA does have a program in place to procure commercial satellite Earth observation data under the 1998 Science Data Buy Program. But the program has not been used by NASA for over a decade. It is time for NASA to initiate constructive dialogue with the private sector to assess the viability of public-private partnerships for the provision of space-based Earth observation data to meet NASA program requirements. Our nation cannot afford to simply ignore the great potential of public-private partnerships to lower costs and improve the quality of Earth observation data. There are many important issues to be discussed at today's hearing, and I look forward to hearing the testimony of our distinguished witnesses. I now recognize the ranking member, the gentlewoman from Maryland, for an opening statement.
Thank you very much, and good morning and welcome to our distinguished panel of experts. I want to start by thanking Chairman Babin and Bridenstine for calling this hearing on exploring commercial opportunities to maximize Earth science investments. I also want to thank in advance our ranking member on the Environment Subcommittee, Ms. Bonamici, for sitting in the chair when I slip away in just a few minutes, so I appreciate that. Earth observations support a myriad of applications to meet critical national needs, whether they be related to national security, weather forecasting, agriculture production, land use management, energy production, or protecting human health. Earth observations also support the scientific research and modeling that we hope can someday provide us with a comprehensive understanding of the Earth and its response to natural and human-induced changes. The collection of Earth observation data has been enabled by sustained federal investments that I hope we will continue to sustain even in the midst of budgetary constraints. Those investments have enabled the development of a robust value-added industry dedicated to turning Earth observation data into usable information that can benefit broad sectors of our economy. Then, too, federal investments in the underlying Earth observations technologies and systems have resulted in capabilities that have enabled a growing commercial remote sensing industry to emerge. So it makes sense to continuously look for new ways in which we can improve our ability to carry out Earth observations and maximize our Earth science investments. Today, we'll explore the extent to which NASA might be able to leverage potential public-private partnerships to carry out its Earth science research and support the applied uses of that research. Truth be told, NASA has always had prior experience in purchasing commercial Earth observation data, and indeed makes great use of the private sector. That was my personal experience, having started out at Goddard Space Flight Center, working on Landsat, but not working for NASA, but working for one of its contractors, Lockheed. And so we've made great use of the private sector and its innovation and creativity over many years. This is nothing new. In fact, in the late 1990s and early 2000s, NASA initiated public-private partnerships for Earth science research, including one for collecting ocean color data called WIFS. I don't know what that, WIYFS. The results from those early projects demonstrated potential opportunities as well as challenges associated with such partnerships. The complexities associated with such arrangements were noted in a number of studies by the National Academies of Science. For example, at least one of those studies noted that the intersection of scientific and commercial interest in public-private partnerships can pose significant challenges in attempting to meet the disparate requirements of stakeholders. This is because scientists value the free and open exchange of scientific data, the precise calibration, validation, and verification of satellite data to ensure accuracy, and long-term stewardship of data for future use and future research. However, that may not always be consistent with a company's business goals and models. In addition, it's clear that intellectual property issues related to licensing will need to be addressed, as well as issues related to data management, data continuity, and calibration if effective partnerships are to be sustained. So today, I'm looking forward to hearing whether, in light of the potential new commercial capabilities in Earth observation, there are productive ways that commercial systems can complement NASA's Earth observation data collection through the use of public-private partnerships. And if so, what mechanisms should NASA use to determine the circumstances under which public-private partnerships can effectively support the agency's Earth science research and applications, and how should those partnerships be evaluated? How can Congress ensure that the potential public-private partnerships do not inadvertently restrict and constrain research in an effort to generate revenue for the companies? And are enacted policies and authorities that enable the advent of commercial remote sensing adequate to address the future needs of both the federal government and the growing commercial remote sensing industry? Well, it's clear that there are many issues that need to be addressed, and we certainly are not going to be able to do any more than begin our examination on this important topic today. This can be a productive area for future hearings of the committee, and I hope we will continue oversight of this area. I would also note that the National Academy's upcoming decadal survey for Earth science and applications is also likely to address a number of these same issues, and I look forward to hearing the results of that survey when it's done. Finally, I would be remiss if I didn't note that we have long had existing productive public-private partnerships in Earth observations. And so for the many contractors and suppliers who've built a formidable array of both civilian and national security Earth observation spacecraft and ground systems for NASA, NOAA, and other parts of the government, you are a testimony to the longstanding commitment our government has had to making use of the skills and capabilities of the private sector, and they are many. I have every confidence that these type partnerships will continue to be productive both today and in the years to come. And with that, I want to thank our witnesses today, and I especially want to thank our two home witnesses, Dr. Samuel Goward, who's the Emeritus Professor of Geography at the University of Maryland at College Park, and Dr. Antonio Busalacci, Professor and Director of the Earth Systems Science Interdisciplinary Center, University of Maryland as well. And I am proud to say you're great Marylanders and you come from great Maryland institutions, and welcome to today's panel. Thank you.
Thank you, Mrs. Edwards. I now recognize the chair of the Environment Subcommittee, the gentleman from Oklahoma, Mr. Bridenstine, for an opening statement.
Well, thank you, Chairman Babin, and thank you for hosting this hearing today. I'm very excited about the panel that's here. I'm very excited about the prospects before our country. In so many cases, what is happening in space today is what's happening in space. It is outpacing, the commercial sector is outpacing what the government has been able to do. And that's very exciting for us to figure out how do we take advantage of what commercial industry is doing. I sit on the Armed Services Committee as well. We've been dealing a lot with the space-based communication architecture. Commercial industry has been providing massive amounts of capacity for our warfighters all over the world. And of course, they've been doing it because we had a need and commercial industry was there to meet that need. They didn't launch satellites because the government asked them to. They launched satellites to make a profit and provide a return for their shareholders. At the end of the day, the Department of Defense said we need that capability, and what's happening now, because of commercial industry, we're getting higher throughput and more capacity than we've ever seen before for our space-based communication architecture, a lot of it provided by commercial that we as a government can take advantage of. So that's an important, I think, analogy to what we're going to talk about today. I would also say that on the NOAA side, we have private companies that are preparing to launch satellites that can do things like GPS radio occultation and hyperspectral sensing. And of course, I read, Dr. Pace, I read your testimony, and you talked about how these technologies, we've been considering commercializing these technologies for a very long time, going back to the 90s, which I did not know before reading your testimony. But now commercial industry is at a point where we as a government can take advantage of these technologies in ways where we haven't before and improve our ability to predict and forecast weather, which is, of course, very important to my district. I come from the 1st District of Oklahoma. This year I've already lost one constituent to a tornado. I've lost constituents in previous years, and I will lose constituents again next year. So taking advantage of these capabilities that have been advanced by the private sector in many ways is critically important to us as a government. I read your testimony, Mr. Shingler, about some of the ways that NASA is already partnering with the private sector. You talked about satellites as a service, and you talked about venture class launch services through the Launch Services Program, ways that we can get things into space more effectively and more cost effective so that we can take advantage of the great things that are happening in commercial industry today. And of course, remote sensing, when you talk about the National Geospatial Intelligence Agency, they're taking advantage of the capabilities of the people that are sitting on this panel right now. And they're doing it because they know that the direction you are going, you're going much more rapidly than they can go themselves. And to understand that, the idea that we can get higher resolution imagery that can provide mensurated coordinates, the idea that we can have more rapid revisit times and even motion pictures, these are capabilities now that the commercial sector is providing that we as a government absolutely must figure out how to take advantage of. Your capabilities are impressive. We need to learn what you're able to do. We need to figure out as a country, as we go forward, you know, there is a lot of talk about what is a global public good, what is a public good. There's a lot of talk about if it is a public good, how do you as a private company protect your proprietary data that you rely on to actually provide a return on investment. These are challenging issues that this panel and other panels are going to have to work through. I want to be really clear when it comes to the Earth Sciences Division at NASA, the Science Mission Directorate. This is an agency that has been very effective in doing important work on behalf of my constituents. They are teaching us more about the Earth so that we can protect our constituents from weather, and of course the things that they have done have done just that. So Chairman Babin, thank you for having this hearing, and to our panelists, thank you for being here. I'm very much looking forward to this testimony.
Thank you, Chairman Bridenstine. Appreciate that. I now recognize the ranking member of the Subcommittee on Environment, the gentlewoman from Oregon, Ms. Bonamici, for an opening statement.
Thank you very much, Mr. Chairman, and thank you to all of our witnesses for being here today. Chairman Bridenstine and I have held a number of thoughtful and engaging hearings examining how NOAA can advance the role of the commercial sector in providing critical weather data to our national weather enterprise. We've discussed potential challenges and opportunities with numerous representatives of the weather community and with Vice Admiral Manson Brown, the Assistant Secretary of Commerce for Environmental Observation and Prediction. The message has been consistent. There are great opportunities to engage the commercial sector in ways to supplement NOAA's observational mission, but we must maintain the core policies, namely free and open access to data, that have allowed our scientific community and the American weather industry to drive innovation and economic growth. Our critical weather data must remain reliable and of the highest quality to protect the lives and livelihoods of millions around the world. In September, NOAA released its draft commercial space policy, which outlines the policies and guidelines for how the agency will engage with the commercial sector. Most importantly, NOAA reaffirms its commitment to adhere to the policy and practice of full, open, and free data exchange as established by current laws and policies to maintain a system of reciprocity for global data. A system of reciprocity that means NOAA receives 3 times the amount of data it contributes, improving forecasts and reducing costs. I'm pleased that NOAA appears to be on the right path to improve engagement with its commercial partners, and I'm looking forward to reviewing the final policy, which I understand will be released in the coming weeks. NOAA has an operational mission, and their data and information are considered public goods. NASA serves a research mission with different challenges and opportunities to engage the commercial sector. And as we've discussed today, there have been partnerships going on for quite a long time. So although there may be an opportunity for NASA to adapt some of NOAA's commercial policies, there's certainly important distinctions that require careful consideration. A common challenge both agencies face is ensuring that data purchased from commercial sources can be shared without significant restrictions. For the most part, the unrestricted access to weather data has been the foundation of the current billion-dollar commercial weather industry, an industry that is the best in the world. It's very likely that data purchased by NASA can be shared in a way to further stimulate future commercial ventures. At the same time, a gap in data continuity in NASA's Earth observations could have serious and detrimental effects on our research enterprise and our understanding of the climate. Both NOAA and NASA are well aware that existing partnerships with private companies carry risks, such as delays in production, launch failures, and cost overruns. For NOAA, any commercial policy that provides critical observational data for weather predictions must consider these factors, as well as the risk to the lives of millions of people across the country. NASA faces similar challenges when developing its path forward to engage its commercial partners, if not on the same scale. Mr. Chairman, again, I'm pleased that we're having this hearing not only to recognize the positive direction NOAA is taking to engage commercial parties, but to identify common ground for NASA to adopt into its own commercial policies. And I look forward to hearing from our witnesses, and I know they have years of expertise among them. We're fortunate to have them here, and I yield back the balance of my time. Thank you, Mr. Chairman.
Thank you, Ms. Bonamici. Chairman Smith's not here. I'd like to now recognize the ranking member of the full committee for a statement, a gentlelady from Texas.
Thank you very much. Good morning and welcome to our distinguished panel of witnesses. I'm pleased that we have an opportunity to discuss NASA's Earth Science and Applications program. As I've said on numerous occasions, NASA is a critical engine of discovery, science, innovation, and inspiration. Earth Science and Applications research is a key agency responsibility. A 2005 study about the National Academy stated that decades of investments in research and the present Earth observing system have also improved health, enhanced national security, and spurred economic growth by supplying the business community with critical information. NASA's Earth Science and Applications program provides a broad array of benefits and applications across the public and private sectors. For example, after the Deepwater Horizon spill in 2010, NASA's project allowed response teams to track the movement of the oil into the coastal waterways. And this was critical in assessing and monitoring the impact and recovery of affected areas along the Gulf of Mexico. Our investment in Earth observations have also spawned successful international cooperation. The Global Precipitation Measurement, or the GPM mission, a cooperative effort by NASA and the Japanese Aerospace Exploration Agency, is advancing our understanding of the Earth-water energy cycles, improving the forecasting of extreme events that cause natural disasters, and extending current capabilities of using satellite precipitation information to directly benefit society. Maintaining and enhancing our Earth science capabilities and investment in the years to come will require that we continuously look for new sources, be they international or from the private sector. Indeed, with growing numbers of American companies launching and operating space-based remote sensing small satellites, this may be an opportune time to assess the private sector's ability to complement NASA's Earth observation systems. I hope our distinguished panel will provide us with an objective assessment of both the opportunities and challenges associated with leveraging commercial offerings. With that, again, I want to thank our witness for being here today, and I look forward to your testimony. I yield back.
Thank you, Ms. Johnson. Now let me introduce our witnesses. Our first witness of today, I want to thank you all for being here. We really appreciate it. The first witness today is Dr. Pace. Testifying first is Dr. Scott Pace, Director of the Space Policy Institute and Professor of the Practice of International Affairs at the George Washington University. Dr. Pace previously served as Associate Administrator for Program Analysis and Evaluation at NASA, as Assistant Director to Space and Aeronautics in the White House Office of Science and Technology Policy, and as Deputy Director and Acting Director of the Office of Space Commerce and the Office of the Deputy Secretary of the Department of Commerce. Dr. Pace earned his Bachelor of Science degree in Physics from Harvey Mudd College, master's degrees in Aeronautics and Astronautics, and Technology and Policy from the Massachusetts Institute of Technology, and a doctorate in Policy Analysis from the Rand Graduate School. And Dr. Scott, our second witness today, is Dr. Walter Scott, Sir Walter Scott, we said a while ago, founder, Executive Vice President, and Chief Technical Officer for Digital Globe, the first company to receive a high-resolution commercial remote sensing license from the U.S. government. Dr. Scott has previous experience serving as the Assistant Associate Director of the Physics Department for the Lawrence Livermore National Laboratory, and as president of Scott Consulting. Dr. Scott earned a Bachelor of Arts in Applied Mathematics from Harvard University and a doctorate in Master of Science in Computer Science from the University of California at Berkeley. Thank you. Mr. Robbie Shingler. He is a co-founder and the president of Planet Labs. Mr. Shingler has 9 years of NASA experience under his belt, helping to build a small spacecraft office at NASA Ames and serving as capture manager for the Transiting Exoplanet Survey Satellite, or TESS, that will launch in 2017. Robbie has also served as NASA's open government representative to the White House and as Chief of Staff for the Office of the Chief Technologist at NASA. And Mr. Shingler has received his Master of Business Administration from Georgetown University, his Master of Science and Space Studies from the International Space University, and his Bachelor of Science in Engineering Physics from Santa Clara University. Good to have you. Testifying fourth is Dr. Samuel Goward, Professor Emeritus at the Department of Geographical Sciences at the University of Maryland, College Park. Dr. Goward has a long history working with remote sensing, beginning his career with NASA Goddard Institute for Space Studies. He then worked at NASA Goddard Space Flight Center, where he helped build the University of Maryland Geography Department. Dr. Goward has served as co-chair of the USGS National Landsat Archive Advisory Committee and is the recipient of the USGS Powell Award, the highest USGS award bestowed upon non-agency individuals. Dr. Goward earned his bachelor's and master's degrees in geography from Boston University and his PhD in geography from Indiana State University. Thank you for being here. And Dr. Busalaki. Our final witness today is Dr. Antonio Busalacci, I'm sorry. Which is better? Busalaki, okay. Busalaki, I apologize. Director of the Earth Systems Science Interdisciplinary Center and professor in the Department of Atmospheric and Oceanic Science at the University of Maryland. Dr. Busalacci previously served as chief of the NASA Goddard Laboratory for hydrospheric processes. Dr. Busalaki also has experience as chair of the Joint Scientific Committee that oversaw the World Climate Research Program, and as the chair of several National Academy of Science and National Research Council boards and committees relating to remote sensing. Dr. Busalaki currently serves as co-chair of the National Research Council's Decadal Survey on Earth Science and Applications from Space. Dr. Busalaki earned his bachelor's in physics, his master's in oceanography, and his PhD in oceanography from Florida State University. I now recognize Dr. Pace for 5 minutes to present his testimony. Dr. Pace, thank you.
Thank you, Mr. Chairman, and thank you for the opportunity, particularly in a joint fashion, to discuss the important topic of how commercial capabilities could be used to the benefit of the nation's earth science investments. I had the privilege of working on Title II of the 1992 Land Remote Sensing Act with Barry Behringer, the former Chief Counsel of the House Committee on Science. In the aftermath of the Cold War, at that time, Title II reformed the U.S. commercial remote sensing license process and removed many commercial regulatory barriers. This reform was successful beyond our somewhat modest expectations, leading to a more dynamic and information-driven global industry. The idea, as has been noted, of buying data from commercial sources for NASA is indeed not new. In 1998, I testified to the House Subcommittee on Basic Research on using commercial data sources in NASA's Earth Science enterprise. At the time, I discussed the need for NASA to consider the needs of other civil agencies in buying commercial data for Earth science needs. The idea was that NASA's capabilities and buying power could be leveraged to support other public missions. New applications of remote sensing data could be demonstrated to accelerate the growth of commercial applications. Looking back from now, the National Geospatial Intelligence Agency, rather than NASA, became the dominant government purchaser of U.S. commercial remote sensing data. Information technologies also advanced rapidly so that more computer and sensing power could be packed into smaller packages. And our concerns over access to adequate radio frequency spectrum for remote sensing also turned out to be somewhat correct. There is, in fact, increasing pressure on spectrum, not so much for remote sensing bandwidth, but from competing demands from mobile terrestrial communications. Rather than a few conventional satellites connected to centralized data management systems, we are seeing dozens of small satellites connecting to highly distributed networks in which even an iPad might be a ground station. And among other changes, sometimes the data files are becoming so massive that moving them to the user becomes less efficient than creating large data cubes that users can query remotely. It's truly remarkable how much data is being put together. Today, NASA's Earth Science Division researchers can propose to purchase commercial data using contractor grant funds when the purchased information is required by or would substantially enhance their research activity. Now, of course, if similar data or information were available in the public domain, there would be no point in making that purchase. And some commercial data may already be available under all government licenses, such as those held by NGA. So there are some potential public-private partnership activities already going on. It's also not news to those here today that budget allocations have been flat or declining in real dollar terms for NASA and NOAA. If NASA were to have the same buying power today that it had in fiscal year '92, when we did the Land Remote Sensing Act, it would have a budget of about $24 billion. At the same time, NASA is now being asked to support more Earth science activities than just those of the Decadal Survey. The success of past NASA missions has created ongoing demands for operational yet exquisite scientific data, and this makes it difficult for NASA to fund new starts for Decadal Survey priorities. For both agencies and companies, it's common to find that each wants to only pay, as we would say, the marginal cost of having a capability rather than the average cost of having a capability. If the dominant market demand is for a public good, then not unreasonably the burden rightly would fall on the government. If the dominant market demand from the private customers, then the burden should be borne by the private sector. In many cases of civil remote sensing, however, like Landsat, there's a roughly even balance of public and private sector demand, which makes a clear partnership and definitions much more difficult, not easier. Major elements, I would argue, of NASA's Earth Science program are likely to remain government-led due to the lack of commercial demand for specialized scientific data, that is, customers outside of the government. Commercial providers will likely not soon replace unique platforms such as those on the A train. On the other hand, where NASA needs can be met by commercial data sources, cooperation with other agencies, such as NGA, can increase the government's buying power. And as has been noted, NASA does have the authorities to do this more extensively. In acquiring commercial data, NASA should ensure that it gets sufficient rights such that the data sets can be shared for scientific, non-commercial purposes. It should ensure that it has sufficient insight into how the data was generated so that peer review can independently assess conclusions based on those data. And I think some of the other witnesses will likely note that there are a variety of rights that can be bought, and it's not a one-size-fits-all situation. There should be procurement on-ramps to enable experimentation and large-scale innovation in parallel with current government systems and international partnerships. We can talk about some of those, for example, for Landsat. In the long term, it will be more risky to pursue only traditional acquisitions without a mixed portfolio that includes non-traditional and commercial procurements. Finally, NASA should continue to be a strong domestic and international advocate of preventing interference to radio spectrum upon which all remote sensing relies. Spectrum protection is and will continue to be challenging due to commercial terrestrial communication demands for more spectrum in the years ahead. Thank you for your attention, and I look forward to any questions.
Yes, sir. Thank you, Dr. Pace. Appreciate it. I'll now recognize Dr. Scott for 5 minutes to present his testimony. Dr. Scott, thank you.
Thank you, Mr. Chairman.
Yes, sir.
I'd like to acknowledge that 23 years ago, with its support for the 1990 Land Remote Sensing Policy Act, this committee set in place the framework that enabled commercial space observation of the Earth to be born and to set the stage for what's turned out to be a very successful public-private partnership. Over 23 years ago, when I started Digital Globe, the Cold War had ended, and the global transparency that had been provided by satellite reconnaissance had contributed to keeping the Cold War cold because it allowed nations to act on the basis of facts, not on the basis of fears. Along the way, the Landsat program introduced the world to satellite imagery in 1972, and this led me to wonder, couldn't those benefits be more widespread? Imagine if there were fewer instances of hunger, thirst, strife, sickness around the world. Wouldn't that lead to increased global stability and a greater quality of life for mankind? So now roll the clock forward. The satellite, high-resolution satellite imagery industry was successfully commercialized and brought to market in 2000, supporting customers that include a wide range: energy, financial services, U.S. allies, U.S. government, online mapping. If you've looked at satellite imagery on your mobile devices, it's probably digital globes. And in many ways, satellite imaging, the satellite imagery industry represents an ideal model for public-private partnerships. In our case specifically, we've been a trusted partner of the U.S. government for more than a decade, most recently with NGA's Enhanced View SLA, which is a 10-year firm fixed-price contract where the government pays for the products and services that it receives, but not for the infrastructure, the overhead, the workforce, or any of the associated costs of a traditional government acquisition. And today we provide NGA with over 90% of their foundational Earth imagery requirements. They get first priority tasking to our high-resolution unclassified imagery, and it can be shared broadly to support operational mission planning, disaster response, recovery, situational awareness. So what are some of the key lessons learned from that public-private partnership? The first one is to balance the needs of the U.S. government with the commercial partner. We make our money by collecting imagery and then licensing it multiple times to different customers for use in different ways. As such, if a customer is allowed to widely and freely disseminate the totality of our products, it undermines our ability to deliver commercial value. And so there are models in which we could make all of a certain type of imagery available for broad sharing, as Landsat is today, but at a higher cost to the government to offset the loss of the commercial opportunity. And the government would need to make that trade-off. The second key point is it's critical to have a predictable regulatory regime that's designed to foster innovation. This is extremely important to us, and I'd like to thank the recent support by this committee on the Space Act that was passed last night, specifically Chairman Bridenstine and Congressman Perlmutter, thank you very much, who championed the remote sensing language that I believe is a needed first step to regulatory reform. You think about it, the current regulations on our industry were written at a time when very few players outside the government were capable of remote sensing. And the world is obviously very different now, where there are billions of people who use the internet to access satellite imagery, and there are hundreds of remote sensing satellites being launched by dozens of nations. The U.S. played a critical role as an international leader in the space industry, And to maintain and extend our leadership, we need a regulatory framework that encourages that leadership and staying well ahead of and not simply achieving parity with foreign competition. So in closing, I want to thank you for the opportunity to describe our unique public-private partnership with NGA. It's been our honor to work with NGA, which is unwavering in its efforts to secure our nation. And we share a commitment to that service, and it's why so many of our employees have chosen to spend their careers at Digital Globe. There's no higher honor than serving those who serve our country, and that's how we live up to our purpose of seeing a better world. Thank you.
Thank you, Dr. Scott. I now recognize Mr. Schindler for 5 minutes to present his testimony.
Thank you, Chairman. And thank you very much to the committee for inviting us here today and having this important conversation. I would like to offer you my thoughts on how a changing landscape and how the landscape is changing in commercial space activities. This suggests that NASA and other government agencies should rethink the nature of their relationship with the private sector. The concept of public-private partnerships needs to expand to be inclusive of the full portfolio of activities where government and private sector efforts overlap and intermingle. A core objective of this suite of activities should be to encourage U.S. entrepreneurial ingenuity, as this certainly is going to be a strong source of U.S. leadership in space in the 21st century. I will speak specifically to opportunities in the realm of Earth observation to illustrate this larger concept, but this same framework is applicable to other challenges and opportunities that we face in space today. Over the past several decades, in parallel to the pioneering work being done at NASA, a new world of sensor technology was emerging, driven by the massive improvement in technologies from the commercial sector, including consumer electronics industries, biotechnology industries, and the internet. What this means is the capacity is to have highly capable, sensitive, long-lived, low-cost components fielded in technology platforms in any location. We see this in our pockets, we see this in drones, we see this in our homes, in our cars. It's a global sensor revolution that's giving us near real-time data about the world around us. So my co-founders and I, inspired to think big at NASA, wanted to bring the sensor revolution to space. So we formed Planet Labs. Our first goal was to leverage the utility of having a distributed sensor network in space, and that is to image the whole Earth every day. And we call that Mission 1. And the purpose of doing that is to make global change visible, accessible, and actionable. To accomplish our goal of whole Earth everyday imaging, we're placing more than 100 satellites into a sun-synchronous orbit. Today, we've launched a total of 101 test satellites over the last 2.5 years, and we are currently operating nearly 4 dozen spacecraft in 2 different orbits. Today, we operate the world's largest Earth observation constellation, and given our pace of development and learning and our planned launch manifests over the next 12 months, we anticipate having the global daily monitoring capability from space operating this time next year. Planet Labs is one of several companies leading a new revolution in Earth imaging. Companies with a similar perspective on innovating quickly with new technology, pursuing a meaningful mission, and disrupting markets and industry sectors. Companies that are privately funded, looking for a commercial market return first before approaching the government. These companies are bringing higher resolution imaging, higher revisit Earth imaging, video from space, commercial weather data, and other capabilities to reality. Much of these technologies, industrial capability that is being developed, lend itself to other missions in space, especially in areas where disaggregation and distributed sensor networks can be best utilized. I am compelled to note that at Planet Labs, we consider ourselves to be in partnership with the civil government Earth observation community every day. For example, we use Landsat 8 data for many critical purposes. We use MODIS data, cloud data from NOAA systems. NASA and NOAA provide a critical foundation for our activities, and without their publicly available data, we would be significantly challenged to accomplish our goals. Moreover, the longitudinal history and reliability of these systems are key for industry to prosper and for scientists to discover a greater understanding of our planet. Since the beginning of the space era in the middle of the previous century, space activities have had 2 extremely strong pillars: the national security space domain and a civil space domain led by NASA. The private sector has evolved to a point where it is certainly a 3rd pillar into itself. Therefore, it is time to rethink a new structure for government-contractor relationship with industry. A new industry-government relationship considers several factors holistically. These factors include government programs that foster innovation by creating white space for new concepts, creativity, and exploration that could lead to new capabilities, products, and services. by the outcome, not the process. Government programs that utilize kinds of agile aerospace methods practiced at Planet and elsewhere to more rapidly advance their internal technology projects and train their professionals for multiple methods of program management. Government agencies who can act as consumers in the market, able to recognize that they are one of many customers in a marketplace of new data and services. Data buys for research and development and validation, and become a solid second commercial customer of a commercial product. And finally, a regulatory environment that is responsive and supportive to the innovations that come from the private sector. A good regulatory environment that has insight, oversight, and foresight to foster commercial innovation. Thank you very much. I have much more detail in the long-form testimony, and I look forward to answering your questions today.
Thank you, Mr. Shingler. I now recognize Dr. Goward for 5 minutes to present his testimony.
Thank you, Mr. Chairman. I guess that I'm here representing the past and what we have or have not learned from it. So I think it's important to revisit Landsat, who I variously refer to as the albatross, as in the Lost Mariner, or the Rodney Dangerfield of land remote sensing, because it has suffered many, many tragedies over the years. The first started when the mission was first described and developed by an NRC panel in 1967, held at Woods Hole, where the discussion of Earth observations led to the decision that land remote sensing would be most likely to commercialize. Unfortunately, that developed from a tradition of aerial photography, which preceded by a century this discussion of Landsat, and actually missed the point of the innovators and visionaries who first conceived of the Landsat mission, which was to be a global monitoring system, not a picture acquisition system. And in fact, that's been missed many times, but actually the first Landsat mission was designed to have 2 satellites to demonstrate how you would develop an operational constellation to monitor planet Earth, as my colleague was just describing. Now, that was back in the 1970s when these designs were being developed, but it's never been captured as a part of the Landsat mission. And in fact, we've degraded since then, at least from my point of view. It's important to recognize that because of this sense that Landsat was most likely to be commercialized as a substitute for aerial photography, it has suffered at least 2 examples of commercialization which have failed. The first of which was in the 1980s when the executive and Congress moved Landsat to NOAA and then commercialized the system with EOSat. That was an experience that all of us involved in the science community still live in fear of today. And in fact, it's one of the reasons when you find scientists hesitating when we talk about private-public partnerships, that the experience with EOSat is clear still in everybody's minds. Now, there are many lessons learned that I'm not going to go over today about what happened in that case, and we should never forget those lessons learned as we look to the future. Because honestly, on the other side, I had been involved in the science data by convening a science panel to select the vendors that were chosen to provide products to NASA for Earth observations in the late 1990s. And we actually had a remarkable series of successes, including the space imaging ICONOS data. And we would have used Digital Globe and did very late in the process, but there were launch issues that had occurred prior to that. So the second time that Landsat suffered a data buy issue is in the acquisition of Landsat 8. And under that process, the first process that was pursued was a data buy in which both Resource 21 and Digital Globe were involved. Digital Globe decided, probably for clear reasons, that they were getting out of that game or before the bidding was selected. And Resource 21 was not selected because there was simply no cost savings involved to the government with the bid that they provided. But that's the second commercialization effort for the Landsat mission. And I can tell you, both of those efforts have put us behind in our science development of the value of this mission to observe the Earth as a result of those activities. So when you talk to the science community, you're going to get a very funny reaction about private-public partnerships, which is not necessarily a bad thing, but you have to understand this history colors the view of the science community in the use of this approach to data acquisition. However, it's important to also recognize that when Landsat came back to the government in the 1990s, that data buy became no longer an issue, but the value of the data for science activity became very clear. And I'm not, again, won't go through the detail of it. I'm out of my time, so I'll stop here. Thank you.
Thank you, Dr. Goward. And now I would like to recognize Dr. Busalaki for your testimony as well for 5 minutes.
Good morning, Chairman Babin, Chairman Bridenstine, ranking members Edwards, Bonamici, and members of the subcommittee. Prior to my coming to the University of Maryland 15 years ago, I was a civil servant for 18 years at the NASA Goddard Space Flight Center. While I was a lab chief at Goddard, I served as a source selection official for the CWIF's Ocean Color Data Buy from Orbital Sciences Corporation that is directly relevant to this hearing. Presently, I also serve as the co-chair of the Decadal Survey for Earth Sciences and Applications from Space, being carried out by the National Academies of Science, Engineering, and Medicine. The report from this study will provide the sponsors, NASA, NOAA, and the USGS, with consensus recommendations from the environmental monitoring and earth science and applications communities for an integrated and sustainable approach to the conduct of the U.S. government's civilian space-based Earth system science programs. Before continuing with my testimony, I should note, though, that I'm speaking in my own behalf today. Nothing in my testimony should be construed as indicating anything about what the Decadal Survey Committee may recommend when a report is published in the summer of 2017. If there's one take-home message from my testimony this morning, it is the need to establish a series of best practices to guide future public-private partnerships for Earth remote sensing, drawing on the lessons learned from the past. So in this regard, and based on my own experience, the following are characteristics of a successful partnership between NASA and a private entity. Firstly, the need to establish an appropriate insight oversight model with the commercial partner. What worked well for the CWIF's science data buy was one where NASA maintained insight but not oversight of the project. Next, to ensure the highest quality of the scientific data, NASA needs to have access to the algorithms and instrument characterization, access to and ability to reuse the data, and establishment of an appropriate data archive. Turning data into information of value to both a commercial entity and to the science community now and in the future requires detailed knowledge of how the raw data are generated, the algorithms that are used to process the data and generate higher-level data products, often combined with data from other sensors and platforms, and control of how the data are archived. Another important aspect is the need for science teams as part of a plan to maximize the utility of the data. The establishment of a science team early in the development of a NASA Earth observation mission is a familiar and well-grounded recommendation. Once established, early science efforts, be it development of a prototype system or synthetic data sets, can contribute directly to engineering and system analyses. They can also optimize algorithms through competition. Such teams provide a conduit to the user community and also provide timely engagement of the research community, which would rapidly expand the user base. With respect to a successful public-private partnership, technical readiness is an important measure of what observation methodology may be ripe for transition. In the case of Earth imaging, as we've heard this morning, there's over 6 decades worth of heritage on the design of such sensors. This has provided the opportunity for significant core competencies to be developed, as we've heard, in the private sector, thus enabling public-private partnerships. Those technologies that are mature are likely the ones that may be most amenable to a public-private partnership. Conversely, the more novel the technology or newer the data stream or observation, the greater the requirement for government involvement in order to draw on a wider base of expertise for sensor characterization, calibration, validation, science data processing, and reprocessing. Lastly, while obvious, it must be stated that the commercial demand and market for the data is key to cost savings to the government. If the government is the sole user of the data, there is little incentive for a public-private partnership. In the example of CWIFS, the cost to the government was reduced by Orbital Science's intent to sell the real-time data to the commercial fishing industry. Transition across basic research to applied research to the development of products and applications is not fast and is not easy. However, the extent to which this can be accelerated in support of a range of societal benefit areas, be they agriculture, transportation, fishing, land use, etc., will determine the non-governmental demand for the data and potential cost savings to the government. In closing, public-private partnerships offer an alternative and potentially less costly method to acquire Earth observations. However, with CWIFS as a guide, a successful public-private partnership may be realized only in limited circumstances and only with the careful attention to the particular needs of both profit-making entities and the science community. Thank you for your attention. I look forward to the questions.
Thank you, Dr. Busalaki. I thank all of the witnesses for your testimony, and the chair recognizes himself for 5 minutes. Dr. Scott Pace. Traditionally, NASA's Earth Science Division focused on one-off research satellites to demonstrate technology and science. Recently, however, NASA was given responsibility for the Sustainable Land Imaging Program and a number of NOAA's long-term satellite observational requirements, including TSIS-1, the Ozone Mapping and Profile Suite, OMPS, and the JPSS-2 Radiation Budget Instrument, and future ocean altimetry missions. How, if at all, do these new responsibilities represent unique opportunities for public-private partnerships?
Okay, thank you, Mr. Chairman. Each one of these missions is somewhat different, and as my colleague was saying earlier, needs to pay attention to the particulars of each case, in particular finding, non-government or non-NASA agencies who want the data. In the case of Landsat, at the risk of continuing the Rodney Dangerfield analogy, I think that the technical risks in providing that data tend to be the most well-bounded, and there are multiple non-NASA users, and that given the right incentives, commercial entities could fund development, test, and operation of those systems. However, that option, I think, has been largely precluded by the intent of Congress that NASA would develop the next Landsat satellite pretty much as a repeat of the earlier satellites. And I would simply look at the NASA Appropriations Conference report for fiscal year 2015, which really precludes any sort of out-of-the-box approaches to data collection. That's why I talk about the need for some sort of on-ramp or parallel activity, maybe revising the science data buy, or maybe looking at some more partnerships with NGA in each of these areas, and to not prejudge what the outcome would be, but maybe have a competition through NGA or through the SDB and see what you get. I would suspect that the Landsat option would come in pretty attractively, but then there would have to be a robust internal discussion in the Congress as to whether or not they wanted to have that on-ramp or really whether they wanted to continue with the current appropriations language.
Thank you, Dr. Pace. And this next question is directed to Dr. Scott and Mr. Schingler. According to the 2007 Earth Science Decadal Survey, an emerging source of data is the commercial sector. In the past, a program of Earth observations was associated almost exclusively with government-managed or government-sponsored projects. Today, commercial sources of Earth information are rapidly increasing in availability and scope. Commercial satellite systems are now reliable sources of high-resolution Earth imagery, and commercial remote sensing companies have greatly expanded their offerings. In your opinion, where does the commercial remote sensing sector stand today, and how can the commercial sector fulfill civil government Earth observation needs? Dr. Scott, you first, and then Mr. Schingler.
So I'd say I'll break the answer down into two parts. The first part is to leverage those data sources that already exist bearing in mind not to break the business model. So we've talked a fair bit about where sharing of data can be bounded by licensing. So, for example, sharing of data to the research community, but perhaps not in a way that undermines the commercial benefit broadly. We have such an agreement in place with NGA, where NGA has quite a degree of ability to share within the government, with coalition partners, with allies, but that does not undermine our ability to serve our other commercial customers with different licensing models. So it's possible for those to coexist. Then I think the second part is to leverage the commercial sector to create data sources that might not yet exist, but which could be created cost effectively, because the commercial sector is able to acquire systems and operate them in a manner that is typically more efficient than a traditional government acquisition. The best situation is certainly one where the commercial provider, if you will, lives in the house that it builds, where it leverages the same system to support government and non-government needs, and so the totality of its business is based on the success or failure of that system. So the incentives of the commercial provider are aligned with the government.
Thank you, Dr. Scott. Mr. Schingler?
The decadal survey for Earth Science was a great step forward, because it was actually the first time that it was done by the National Academies on Earth Science, and so it really did provide a prioritized list of the data that needed to be collected from a scientific basis. Within that, they had a call for venture class missions, and which, in my opinion, is one of the greater things that we can do in order to lower barrier of entry for new scientists to come in to understand our planet. However, the sensors were not there, the industrial base was not there in order to reach a price point at the time that the National Academies report was released. Today it's very different. You could actually see that launch access to space is still a major barrier, and part of NASA Launch Services, together with SMD, is helping to fund $17 million for 3 new commercial nano launch capabilities and access to space. That's a really, really good step forward. But when you combine those things together, you could think about a portfolio of different scientific activities, some of which bring about a rapid amount of capability, taking more risk, but at a much decreased cost. And then with that, that can then help smooth our future critical path into the future. Thanks.
Thank you, Mr. Schingler. Now I'd like to recognize the gentlelady from Maryland. Oh, Ms. Bonamici. Okay, I'm sorry.
Thank you, Mr. Chairman. Thank you, witnesses, for your testimony. Dr. Pace, you said in your testimony that in acquiring commercial data, NASA should ensure it gets sufficient rights so that data sets can be shared for scientific non-commercial purposes. It should also ensure that it has sufficient insight into how the data were generated so that scientific peer review can independently assess conclusions based on those data. So Dr. Goward brought us some lessons from history. So how is that accomplished? Is that through regulation or through really good negotiation? I mean, how does NASA ensure that it gets those rights and that it has that insight?
I think has been described actually by Dr. Scott, that there are a wide variety of rights that you can buy. In some ways, the idea of purchasing data is kind of a misnomer. What you really don't buy a computer program, you buy a license to use that computer program. So the question is, what's the negotiation over the bundle of rights you can get? And NGA, of course, has a way of negotiating certain rights. So it becomes a competitive aspect, and there's a cost trade-off. It becomes part of the make or buy decision for the government. So the government goes in and says, I want to acquire certain kinds of information and data to do my public mission. I can decide to build a government satellite to do that at a certain amount of cost, sometimes more than what the private sector would do, but then I have more flexibility downrange. Or I can decide to buy a bundle of licensing rights to go get the same sort of thing. And this is where having a large buyer like NGA can be leveraged, for the benefit of the government. So I think it's fundamentally a business analysis. Is it, make or buy? And then fundamentally, it's a legal negotiation and a competitive process, and that companies should come in and be prepared to bid a range of activities. Now, if it's something like a decadal science priority, I would say that there would be a high priority on having very deep metadata, that you get because you're trying to do something at a very, very much cutting edge. There may be no commercial counterpart for that decadal science priority. And so then the question of build or buy becomes really of, can the government do it more efficiently, or can a private sector part do it efficiently?
Thank you very much. Dr. Buscalaki, for a public-private partnership that supports NASA's requirements for basic and applied research, how does that compare with a public-private partnership that could support NOAA's operational weather mission? When we're considering evaluating those public-private partnerships, what are the differences and how would we evaluate those?
Thank you very much. First, there's a clear difference between NASA research and NOAA operations. They're often seen as parallel, but there are significant differences. Let me draw on the NOAA operations example. In order to support operational numerical weather prediction, the demands of providing a forecast on timescales from minutes to a day or a couple of days into the future require those observations to be taken down, ingested into the model, and those bits can actually then fall on the floor after they're used for supporting numerical weather prediction. Now, we've learned that those data do have value for other applications. However, in the case of NASA research, when you're looking at timescales from days to weeks, months, and years, you're very concerned about the stability, the continuity, insight to the algorithms that you may not have because of proprietary reasons when dealing with the private sector. So there's a difference in timescale and a clear difference in the need for stable, continuous, calibrated, and validated records on the research side.
And that leads me to my next question for Mr. Shingler and Dr. Scott. Many Earth science objectives require long, stable, uninterrupted time series measurements. Can the commercial market support such a long-term operation? With NOAA weather data, for example, it's important to have open, publicly accessible data so our other countries will share their data with us, and American public has access as well. So what happens if the U.S. buys data and then can't share it? If NASA contracts out its Earth science work with a predictable, reliable funding stream, would the private sector accommodate requirements to make that data public?
So the commercial community can absolutely help to support time series measurements in a reliable and predictable way. In no other case that our commercial customers demand it as well. So that is absolutely something that the community can do. When it comes to NOAA and when it comes to the license around publicly available data, I think that needs to be incorporated into the business models of the companies. So perhaps you could use an example of what we know in the aerospace community with GPS and selective availability. So there could be a downgraded version that is available to the U.S. government that is bought and then made as open data, with then higher fidelity data for some of their commercial customers. So that is something that you can then coexist and come up with a sustainable business model around while you still actually create a public good and provide that service to the government.
Dr. Scott?
Well, in terms of data continuity, we've been providing data since 1999, which relative to the Landsat program, it doesn't go back to 1972. But for the commercial remote sensing industry, is certainly the longest uninterrupted record of continuous observation. I'll also mention, just as an aside, the commercial sector has put quite a degree of effort into a high degree of fidelity and calibration of that data, leveraging, in fact, a lot of the work that NASA had done over the Landsat program. In terms of open availability, I think open it feels very binary. It feels like it's either completely open or it's not open at all. And as Dr. Pace was saying, there's actually, it's very analog. There's a wide range of gradations. I'll use for Digital Globe as an example. We make data available to web portals, Google, Apple, and others, that you can download on your mobile device. You say, well, that's open. How does that not undermine the commercial market for Digital Globe's data? Because there are certain rights and certain limitations on the data that's available that mean that it's possible for us to, in a very granular way, enable data for different customers with different rights to meet their specific needs. So one could imagine, for example, making data available that had rights for sharing for research purposes, but not for commercial purposes, or rights that were available for sharing with other nations, but not for sharing for commercial purposes. So I
Thank
think
you very
it's-
much, and my time has expired. Thank you.
Thank
I
you.
yield back. Thank you, Mr. Chairman.
Yes, ma'am. Thank you. Now recognize the gentleman from Oklahoma, Chairman Bridenstine.
Well, thank you, Chairman Babin. I'd like to thank all of our panelists for being here. I was hoping maybe next time we could get a few more degrees on the panel. With all these doctors, for a second I thought I was in a hospital, but I'm glad I'm not in a hospital. So it's great to see all of you. Dr. Scott, I wanted to, number one, thank you for the service you've already given to this great country. You took great risk upon yourself and created something that brought us to where we are today, which is why we're even having this discussion. So thank you for your service and all you've already done. Dr. Goward, I wanted to address your comments earlier. I read your testimony, and I had a different takeaway from what I just heard. And I wanted to see if maybe I could have you maybe enlighten us a little more about what your thoughts are going forward. One of the things I read is it says, today, with the maturing of new sensor and satellite technologies, the opportunity exists to fly at least 4 Landsat observatories at the same total cost as a single satellite, which uses the traditional technology of Landsat 8. So when you talk about these new technologies, your testimony that I read sounded a lot like Mr. Shingler. Can you share with us your thoughts? Do you believe we can move towards a Landsat kind of commercial capability? Can you turn on your microphone, please?
Thank you. I'm not sure it would be commercial. I mean, that's really outside of my purview in many ways. But my former student and colleague, Darrell Williams, and I put together an EV2 proposal through Global Science and Technology. And in that, we worked with Surrey Satellite. And it's a U.S.-based company at this time. And we did a proposal which showed that for about $130 million, we could build a prototype system. Wouldn't be fully complementary with Landsat, but sufficiently to supplement and complement Landsat. And that's substantially less than what this last Landsat 8 has cost us. GST then went on to do further work with Surrey, and a fully complementary Landsat mission was able to demonstrate that for about $250 million, they could build a fully complementary system. It's my view that we should give this a try now and get that technology out on the table because, again, from our scientific experience, I don't believe that the commercial potential of the Landsat mission will be realized until we get, as my colleague to the right mentioned, daily repeat coverage.
Right. Okay.
The land dynamics just happen too fast, and you don't see it every 16 days when clouds block you at least 50% of the time.
Okay. I'm running out of time here. I wanted to move to Dr. Pace. You mentioned in your testimony that the Earth Sciences missions the demands have grown and the requirements have grown, and yet there are opportunities where we can share the cost because there are non-NASA customers potentially. And you mentioned Landsat as one of those places where we could do commercialization, but then you mentioned that it was precluded by Congress. I'm very interested in this. Why did Congress preclude this?
Well, my understanding is, if I read the NASA Appropriations Conference report, it states, quote, the committee conference does not concur with various administration efforts to develop alternative out-of-the-box approaches to this data collection, referring to Landsat, whether they are dependent on commercial or international partners. And so essentially this said, build another Landsat satellite similar to what you've already been building. And I have a sense of deja vu with this because I was the guy at the Commerce Department who was told to get Landsat out of the Commerce Department at that time, so I wasn't very popular with my other agency colleagues. One of the things that we looked at were alternatives for LightSat or SmallSat versions of Landsat in 1992. We were taking advantage of some SDI technologies that had come out of Livermore Laboratories and other places. And so there were theoretical designs, and they were all just that, theoretical, but for LightSat versions of Landsat that Dr. Goward was also talking about. And so it strikes me that today, given the greater design maturity and experience we have with small satellites, that we should go back and be looking at more innovative ways of doing things. The reason we wanted to look at small sats back then is we felt that cost growth would be a problem for any agency that took over Landsat. And so that's why I said in my testimony that if we simply continue with only the traditional practices, that is actually going to be more risky than having some innovative options in the portfolio that could lower costs in the longer term.
Okay, and I'm out of time, Mr. Chairman, but as far as the appropriations, I guess, conference report, that language is unfortunate. I don't think that necessarily reflects the view of a lot of people that serve on this committee on both sides of the aisle. So I need to delve down into that a little bit more. Maybe, Mr. Chairman, if we could do a second round, I'd appreciate that. Over to you. Thank you.
Thank you, Mr. Chairman. I'd like to now recognize the gentleman from Virginia, Mr. Byer.
Thank you, Mr. Chair. And I'd be happy to defer to the ranking member from Maryland if she would prefer that.
Thank you very much.
Sorry about that.
Thank you very much. Just a little confusion here. We're just moving around. I'm curious, OSTP's National Plans for Civil Observation includes an action entitled Explore Commercial Solutions, where federal agencies are actually tasked with identifying cost-effective commercial solutions to encourage private sector innovation while they preserve the public good nature of Earth observations. In particular, agencies are asked to consider a variety of options for ownership, management, and utilization of Earth observation systems and data, including commercial data buys and commercial data management. In developing such options, agencies are to preserve the principles of full and open data sharing, competitive sourcing, and best value in return for public investments. And I'm curious as to the viewpoints, if we could quickly, should be the first steps in implementing this kind of guidance from OSTP. Starting with you, Dr. Pace.
Well, I think one of the things that ought to be looked at is look across all of the agencies that are involved in the sort of remote sensing. This means looking at what NGA is doing with its GeoInt strategy, look at what NOAA is being asked to do, look at what NASA is looking to do. So don't look at it as simply an agency, single agency only sort of thing. It's really across the administration. And then you should be able to see what portfolio mixture am I doing? Am I just, what things are being done as large traditional satellites? What areas do I have innovative, smaller satellites? And what areas do I have a mixture of small data buys or licensing and pilot programs? So I'm not trying to say what those numbers ought to be. I'm saying there ought to be a portfolio, and then there ought to be a discussion within this committee and within both sides of the Hill as to what the right amounts of effort ought to be in those areas. But you ought to have a mixed portfolio, not just a single one. And so I don't think that the OSTP direction is quite being followed at point. I also don't think that the decadal survey recommendations to look at more innovative sourcings are being followed. And I think that NASA in particular is being burdened by large operational ongoing missions that there's all kinds of good reasons why they're there, lack of appropriation allocations for NOAA, problems with the 302B allocation, all those sorts of things. But nonetheless, NASA is getting more burdens than simply you would expect from its decadal science priorities.
Dr. Goward, do you have an opinion about this?
Through this, thank you. Just sort of four general guidelines in my experience over the years is, as Dr. Bushalashi had mentioned, insight versus oversight in private-public partnerships is really critical. Otherwise, private industry gets hampered in innovating in their work. But from the other side, private industry has to be willing to participate in arrangements where the observations are available for no-cost distribution. Particularly for the Landsat mission, we've gone from practically no usage of the historical record to usage that's in the millions over the last 2 to 3 years, because USGS has been willing to provide low-cost and no-cost access to the data record. Honestly, one of the limitations on EOSAT was that they were not allowed to compete in the applied commercial marketplace, and this was a serious problem for them. That company was unable to really build on their capacity to develop the commercial marketplace. They were prevented from doing so.
In the time that I have remaining, do any of the other witnesses have an opinion about OSTP's guidance and how we can begin implementing that guidance?
I'd say one of the first things to do is look at what the industry is both doing and capable of doing. There's often a tendency within government to make assumptions about the industry that are in fact not founded in fact. And a good place to start would be to reach out to the industry and find out what the industry thinks, what the industry is doing, what the industry is capable of doing.
And Dr. B, because I'm butchering your name.
That's fine, I'm used to it. So I've already spoke to the issue of the heritage of the methodology. In the case of CWIFs, with respect to the data access challenge, in order for orbital sciences to market ocean color data, NASA did not have free and open access to the data. And overall, this data access arrangement worked well for research. Researchers had to register and verify that they were only using CWIF's data for research and not for commercial purposes. And even though most of the research with CWIFs was done in delayed mode, we even still within the rights of the data license had access to the data in real time for certain cruises. So going forward, any public-private partnerships need to develop a cost model based on data latency, archival, access, and resolution. It's going to be really really important to tackle those issues.
Thank you very much, and I yield the balance of my time. Well, I don't have any time, but I yield it anyway.
Thank you, Ms. Edwards. Let's see, I'd like to recognize the gentleman from Arkansas, Mr. Westerman.
Thank you, Mr. Chairman, and thank you to the panel for being here today. Dr. Goward, you talked about Landsat being the Rodney Dangerfield, but I would like to give it maybe a little bit of respect today. Having worked in the forestry industry, I've seen how the imagery can be used. We've had developments in the analytics, being able to look at the images and gain more from the images. In a wintertime photograph, you can tell coniferous trees from deciduous trees, and then now through spectral imagery, you can look at the different signatures of the colors of the leaves and get a species distribution through it. So I know that the analytics have advanced, but how would you say the image resolution and quality of data has changed for Landsat over its 43-year history, and maybe just briefly Landsat 1 versus Landsat 8?
The changes have been subtle. The changes occurred between Landsats 3 and 4, when we went from one type of a sensor, MSS, to thematic mapper, TM. And then with the OLI on Landsat 8, a number of changes occurred, additional bits of data to characterize illumination conditions, narrowing of the bands to increase avoidance of atmospheric contamination. So they may be subtle, but they get critically important information that allows us to more and more reliably evaluate forests, agricultural production, other features that we just simply get better at as we refine our instrumentation.
So we've got a long record of continuous and comparable observations that has allowed users to document changes to the land surface and other features over decades. So what are the advantages and disadvantages of deploying Landsat instruments on other satellites, whether they're government or commercial, instead of recreating the same Landsat satellite as the one vehicle for U.S. moderate resolution land imaging?
I see no reason not to deploy an equivalent instrument on a variety of platforms. The things you have to be careful about are the orbital patterns, whether you're in a sun synchronous or in a solar variant observation condition. But you're certainly not constrained to a single platform.
So you think we can maintain the aspects of the data continuity with different platforms?
No, absolutely, and it's more at the detail level of the instrument characteristics that's critical.
Okay, so the cost of Landsat 8 was about $1 billion, and the administration is now preparing to develop Landsat 9. I think the last I saw, 2023 launch for Landsat 9, which is essentially a clone of Landsat 8. Is there a rush to develop Landsat 9, or does the government have the time to evaluate all options for satisfying these data requirements? And what would you recommend NASA do?
It's an interesting problem. The design life for Landsat 8, from an engineering point of view, is 5 years, so that by the time we get to 2023, we're over 10 years. Now, do we suffer a failure in between time? I don't know. We certainly had problems with Landsat 7 early on, and it could happen again. So are we in a rush? Should be, because we should move that timeline for the next launch to an earlier date, if at all possible.
So how many Landsats are we getting imagery from now? Are there still 2 collected?
Still 2.
And what, those are 8 and?
7.
Okay.
And 7, of course, has a partially functioning mirror system.
Okay. And with that, I'll yield back, Mr. Chairman.
Thank you, Mr. Westerman. Now I'd like to recognize the gentleman from Virginia, Mr. Byer.
Thank you, Mr. Chairman. And I'd like to thank both chairmen, both ranking members for putting this together. And thank all of you for coming. It's been fascinating. Mr. Schingler, probably a stupid question, but you mentioned that you have 100 doves up in a single sun synchronous orbit. Are these spaced all around the globe, in the orbit itself? And is it really just a single orbit, or a single orbit for each dove?
Yeah, let me clarify. So over the last 2.5 years, we have launched 101 satellites on 9 different rockets. All of those have been as secondary payloads, and the majority of them have been through the International Space Station. And the International Space Station is in a 52-degree orbit, so it's not in a sun-synchronous orbit. Over the next 12 months, we have a number of launches, including one that is a dedicated rocket that is going to our ideal orbit, which is a 475-kilometer sun-synchronous orbit. And that one launch in and of itself will be able to allow for us to have daily coverage. And the way that that works is we distribute the satellites along track in one particular sun-synchronous orbit, and as the Earth rotates underneath it, our satellites act together kind of like a line scanner in order to image the entire surface of the Earth.
The line scanner is a great image, so thank you. And the size of the satellites?
The size of our satellites are 5 kilograms. They're in the 3U form factor, so it is one person can pick it up.
Yeah, very cool. And Dr. Gower, your last recommendation said the NASA and the U.S. private sector need to move away from increasingly expensive single satellite builds towards lower cost, high temporal repeat, Landsat class observatories, et cetera. Is this what Planet Labs is doing, or is this what Digital Globe is doing?
What Planet Labs and Digital Globe are doing are not the same thing. What we're really talking about for a Landsat system is one that covers 4 different parts of the electromagnetic spectrum, and some of those require a more complex platform than what, for example, Planet Earth will be flying. And when I mentioned the lower cost small sat alternative, we're talking about more on the order of 300 to 500 kilogram satellites rather than 5 kilogram.
Okay, great. Yes, Mr. Schingler.
Yeah, absolutely. The Landsat platform is really quite exquisite in its spectral capability. And that is something that we have longitudinal information over the last 42 years and want to continue moving forward. I think part of the concepts is it may be possible to launch an instrument that does not do all of the spectral bands in one satellite, but instead you can have a couple of different satellites that then focus on the phenomenology that we want to continue as a global community with Landsat.
One of the things I've been impressed by today, with including all these degrees, as Chairman Bridenstine noticed, is how many of you have moved back and forth from government to private sector. Dr. Pace, do you have any concern with your NASA and your private sector perspective that there be a loss of in-house expertise as we outsource more and more to the commercial sector?
That's a great question. I think that's actually really central to thinking about what do we want NASA to do to be a smart buyer. I think NASA should always have 1 or 2 spacecraft builds in-house that they do themselves, so they make sure they have that hands-on expertise. At the same time, I think that NASA is comfortable and with the idea of buying and relying on the private sector and doing commercial data buys. And I think as NASA has been asked to do more and more missions without really an increase in its top line, I think it's going to become more incumbent on them to find ways of partnering with the private sector. So I would first say make sure they have expertise in-house at places like Goddard, but also make sure that you start relying more on the private sector to acquire the data. And as Dr. Scott said, the best way to do that is to ask industry. Too often we can assume what industry can do. And it's perfectly possible for industry not to be able to meet requirements at a certain point in time. So it's always important to have a backup plan. Having a primary plan of a conventional spacecraft, okay, but make sure you also have a backup plan or an alternative in doing something more innovative. And really, I think the agency should be doing both.
Great, thank you. Dr. Busolacci, you only have a minute, but you are deeply involved in CWIFs. Was that cost effective? And in using orbital sciences, was there added value gained from partnering that perhaps offset the extra cost?
Well, CWIS was a grand success from the terms of the quality of the science data we got, and the cost to the government was actually less as a direct result of the private sector data buy. Now, whether or not orbital sciences made a profit, I'm not the one to speak about that in Virginia, for example. But again, it was a grand success from the science point of view. But what we don't realize oftentimes is how important the engineers at Goddard, the role that they played. Even though this was technically a data buy, there were a number of challenges that came up. The mission was delayed by 4 years, and Goddard engineers in the end provided considerable support on the engineering side for power system, attitude control, navigation system, component quality. We had a very good working relationship, but the point was that as opposed to a number of the topics here this morning, there was not a lot of heritage in the instrument. There was the prior coastal zone color scanner, but beyond that, there was a novel lunar calibration. So there was really the need for expert engineering support from an organization like Goddard.
Great, thank you very much. Thank you, Mr. Chairman.
Okay, yes, I'd like to recognize the gentleman from Colorado, Mr. Perlmutter.
Thanks, Mr. Chairman, and Dr. Scott, long time no see. Appreciated the tour last week of Digital Globe, and I guess my question, I'll start with you. You've got this giant library of information. Who gets access? Who curates it? How does anybody figure out all the stuff that's in there?
So we have about 100 petabytes or so of data. It's accessible in the cloud. It's cataloged by an increasing amount of metadata, starting with just when it was collected, but growing to include a lot of information about what's actually in the image. And we've exposed that to our customer community via something we call a geospatial big data platform, which is fundamentally about not trying to take these huge data boulders and say, here's 100 petabytes of data, good luck finding a place to put it. Instead, enabling people to access data in the cloud with a set of algorithms that are wrapped around it to enable exploitation, and a growing ecosystem of partners who contribute those algorithms to enable the exploitation.
So if I wanted to see something involving the soils in some country in Africa, how do I get that information to you, and then how do you provide me that slice of information?
So there are a couple of ways of gaining access to that. If you're interested in viewing the data, just looking at the data, there are web services where we expose that data to you over the web. If you're interested in performing analytics, you can bring your algorithms or use algorithms from one of our partners like Harris, who offers the ENVI toolkit, an image processing toolkit, and perform that processing in the cloud. We have a set of application program interfaces as well as user interfaces that allow you to search for what's available in that particular region and then drop that data into your Amazon S3 bucket for subsequent processing.
I guess what and I appreciate that. So you, Digital Globe, and to the other panelists, please jump in if you want. We're accumulating lots of information out there. And we don't know all the potential users of that and precisely what they want to do with it. So if I am the United States government, let's say I'm the Air Force, I pay you some certain fee for access to all of it anytime I want it, and then some other user of the library may have a much more limited cost and, library card that allows just access to certain things. Is that how it works?
I think that's a great model, actually. It's sort of a customized library card with rights that are consistent with how you intend to use the data. We support a range of business models. Some of those business models involve the actual delivery of data. Other business models involve you get a library card for data analytics, and we receive our compensation in any of a number of ways. Some of which are revenue share based, some of which are subscription fee based.
Okay. So to all of the panelists, if there were one or two things that we as members of Congress could do to make sure that the technology that you all are developing, whether it's on the information side or flying the satellite side or the optical pieces, what could we do maintaining security for the nation, yet allowing you to continue to grow the commercial side of this thing? Mr. Schengler.
So I think the first thing is we should figure out a way to relatively quickly get access to the commercial capability that's there and to engage in a dialogue to really understand more, not just what the product is, but the capabilities of industry. That will help to inform strategies around procurement and other things into the future. And secondly is for things into the future, we should look at other transactional authorities, which do allow for the commercial entity to continue to build their commercial service while relatively quickly sell a capability to the U.S. government.
Okay, Dr. Pace.
I would add that you should probably be looking beyond just the initial data acquisition and the satellite side itself, and to think about where could commercial providers be part of the data archiving and processing and analysis function, the cloud. That is not something which is a government unique function, and there's also systems where commercial users could share, the same hosting infrastructure, and that's a whole nother market, in and of itself. It's just data. It's not particularly specialized. The second thing I would mention, this is probably a subject of a different hearing, is making sure that NOAA's commercial licensing and regulatory process responds to the changes in technologies and markets that have been going on. The regulations that were written in the early 90s really, in many cases, have become a bit outmoded. There's a lot that's really good, but there's a lot that's really largely irrelevant today. And I think that kind of regulatory responsiveness is a subject that the industry needs.
Thank you, and I yield back to the chair.
Thank you. Now, we're going to go back through for a second round of questions, and we're going to limit this to 3 minutes, if that's okay with everyone. So my first question would be to Dr. Pace. In your testimony, you mentioned that there's a need to protect the electromagnetic spectrum used by remote sensing and GPS. And if you would, please explain in more detail to the committee.
Well, sir, for example, remote sensing is crucially reliant upon things like GPS to provide the actual location of the data. So if there's interference to GPS, there's interference to the remote sensing industry. There's also great pressure on all space spectrum by commercial communications. Everybody understands the importance of mobile broadband, the importance of that to the economy and growing the economy. But also there are unique functions that are under great pressure. One area in particular that's come up recently, and I'm sorry to use the phrase 6 to 9 gigahertz, there's some high frequencies that are being talked about for on the Senate side. And this covers a lot of microwave sounders that are used by multiple weather systems. And you can't move to other areas. The water molecule doesn't vibrate in some places. It's not flexible. And so I would suggest paying attention to spectrum as an underlying need of the industry, particularly for critical sensors that really can't be moved anyplace else.
Thank you. And then This would be a question for Dr. Goward and Dr. Pace. Does the U.S. government have a requirement to maintain 1 or 2 Landsat satellites at a time?
Undefined.
Undefined? Mm-hmm. Okay. That answered that. How about Dr. Pace? Same thing, huh?
Nothing to add. It's, that's been part of the long story of Landsat.
Okay. And then real quick, in the next 10 years, what major developments do you believe will be made in commercial remote sensing? And could these developments be used by NASA to improve their imaging efforts or decrease the cost of remote sensing to the government? And if one of you would be glad to answer that, I would appreciate it. Dr. Scott?
Well, I think there are a number that have already been made. This may actually be relevant to one of the earlier questions. Our most recent satellite launch, Worldview 3, incorporates 16 spectral bands of high-resolution data plus an additional 11 spectral bands of 30-meter resolution atmospheric data. And that was done leveraging technology that had been developed for the Landsat program, but at a very small fraction of the cost of a Landsat satellite. That's just an example of the sort of innovations that are happening in the commercial sector that I would encourage the government to understand better in making its future decisions.
Okay. Thank you. I'd like to recognize Mr. Perlmutter again from Colorado.
Can I pass to Mr. Bridenstine as I'm collecting my thoughts here?
Certainly.
Okay.
All right, I recognize the gentleman from Oklahoma, Chairman Bridenstine.
So you're giving me all 3 of your minutes? Is that what's going on here? No, I'm kidding. I'll take my own 3 minutes. Thank you, Chairman and Mr. Perlmutter. Couple of thoughts I had. You mentioned, Mr. Schingler, the exquisite spectral bands and capabilities from Landsat. And maybe that's not your area of expertise, but you could have a distributed architecture or disaggregation where you could have different satellites doing different things. I heard, Dr. Pace talk about, in his testimony, he talks about maybe not commercializing Landsat, but using other sources to gather data. Is it possible, when you think about Landsat and the commercial opportunities that are out there right now, can we gather similar data that would be useful given the exquisite spectral bands that Landsat uses? Can commercial provide a resource in addition to Landsat? Dr. Pace?
Yeah, I think it can, and I think it would make for a more robust series. Landsat data continuity is one of the precious things that the science community has and rightly wants to guard. So having additional satellites, has been mentioned, the idea of a single Landsat was never the original idea. It was always to have this kind of continuous observation. That to me sounds like a service that could be provided with maybe government as a foundation, but with complements from the private sector in a way that I would argue is analogous to what's been talked about with GPS radio occultation.
I noticed that in your testimony, and thank you for bringing that up. I was not expecting that, but that's something we've worked hard on this committee to have radio occultation move alongside the other great capabilities that are being provided by NOAA to move alongside, and we've actually carved out some funding in our bill here on this committee to make sure that NOAA could purchase that data, and of course working with Dr. Voles and Admiral Brown on those capabilities has been a great experience. One last thing with my last 50 seconds, and maybe this is a question for Dr. Scott. We heard Dr. Pace talk about consistency in the regulatory framework coming from the Department of Commerce, coming from NOAA. Of course, that's critically important to this kind of industry. You make investments, and those investments are for your shareholders. At the same time, you're signing up contracts. When those regulations change in midstream, that can have negative consequences. Can you share with us if there's anything we can do to ensure that there's, maybe we can, maybe we can't, but how does that affect you as a business owner?
So when you build satellites that take a few years to build and operate for a decade or longer, and have invested billions of dollars in the course of doing that, the stability of the regulatory environment is absolutely essential. You need to know, and your customers need to know, that they can rely on continuity of service and that there won't be variability subject to essentially the whim of a government agency. We've been fortunate that we have enjoyed to date an environment where, while it has not necessarily been as forward-leaning as we would like, it's been stable. The ability of that regulatory environment to, instead of react to, but rather enable industry to anticipate market needs, that's something that we would like to see change. The pace of technology is moving far faster than the regulatory environment that was conceived back in the 1990s can remotely keep up with, and that's really one of the biggest impediments to the industry going forward.
Thank you, Mr. Chairman. I yield back.
Yes, sir. Thank you. Now I'd like to recognize the gentlewoman from Maryland, Ms. Edwards.
Thank you, and I'll be brief. I'm just curious to know if there are some markers that can help us determine when and if NASA should use public-private partnerships for data collection. Is there, some one point, and then how should they be evaluated? Because I think we've gotten a handle on how we evaluate NASA-driven, internal-driven projects. How do we evaluate public-private partnerships? And if I could start with Dr. Scott to Mr. Schlingler to Dr. Busalaki, in that order, and do it as quickly as possible. How to determine when and if, and how to evaluate them.
Probably the simplest phrase is start with asking. So start with exposing to industry what the needs are, and at the same time engage in a dialogue with industry to understand what the capabilities are. One of the reasons why we have historically been able to acquire satellites very cost effectively is that we approach the problem from both ends. We approach it from the standpoint of what is the technical capability, and then what are the business needs and the business opportunities, and we look for the intersection of those, as opposed to approaching it unilaterally from one side and say, well, here's what we want, never mind the fact that it's nearly impossible to achieve it. We look for the intersection.
So for when to evaluate it, or for when to approach public-private partnerships, I think you first do need to evaluate it first before you get into a complex arrangement between industry and government. And that valuation, just exactly as Dr. Scott is saying, should be based on the service as it is today and the direction of where it's going. And it may not be from the traditional requirements-driven approach, but more of a capabilities-based approach. And that the assessment of the data shouldn't be necessarily taken by itself, but actually in conjunction with other data assets that are already there.
So about 4 main points. As I mentioned, heritage, NASA is very good at assessing technical readiness. What is the reduced cost to the government, and what is the market demand in the commercial sector? And then evaluating what is the elimination or reduction in the financial and operational risk, what is the increased efficiency to be had, and what is the reduction in the fixed costs. I say those 5 main things can be evaluated.
Thank you. 25 seconds to spare. I yield.
Thank you. Appreciate it, Ms. Edwards. And I'd like to recognize the gentleman from Colorado.
Thank you. Thanks, Mr. Chairman. Dr. Busalaki, just a question, and congratulations, I think, are in order for you to co-chair the decadal. And I got to tell you, before I ever got on this committee, I never heard the word decadal before, and I never was quite sure. Apparently, it's every 10 years. It doesn't have anything to do with decay, does it?
No, but our report will be done in much less than a decade.
All right. So my question to you is, as a co-chair with Dr. Abdelati from the University of Colorado, by the way, how are you going to be focusing on how the data is collected, or what types of data are collected, or both? I mean, can you share what your focus of the committee is going to be?
So I'm not being facetious. It is all of the above. It will be looking at what sensors or what missions were in the queue from the previous decadal survey that have yet to be realized, what new science and applications may be possible going forward, and as we've been hearing here, what role can the private sector play, and what are the new technologies? Right now, the Academy is spinning up a report that will be out before our report on CubeSats. And so I fully agree with Mr. Schingler. access to space is a key issue. And if we can lower down the cost to access to space, the potential is there for these CubeSats to be up there and really change sort of our approach. So again, the short answer is yes to all of it: existing science, new technologies, and commercialization in the private sector.
Thank you, Doctor, and I'll yield back to the chair.
Thank you, Mr. Perlmutter. I want to thank the witnesses for their testimony and the members for your questions. The record will remain open for 2 weeks for additional written comments and written questions from members. And with that, this hearing is adjourned.
And we certainly are not going to be able to do any more than begin our examination on this important topic today. This can be a productive area for future hearings of the committee, and I hope we will continue oversight of this area. I would also note that the National Academy's upcoming decadal survey for earth science and applications is also likely to address a number of these same issues, and I look forward to hearing the results of that survey when it's done. Finally, I would be remiss if I didn't note that we have long had existing productive public-private partnerships in Earth observations. And so for the many contractors and suppliers who've built a formidable array of both civilian and national security Earth observation spacecraft and ground systems for NASA, NOAA, and other parts of the government, you are a testimony to the longstanding commitment our government has had to making use of the skills and capabilities of the private sector, and they are many. I have every confidence that these type partnerships will continue to be productive both today and in the years to come. And with that, I want to thank our witnesses today, and I especially want to thank our two home witnesses, Dr. Samuel Goward, who's the Emeritus Professor of Geography at the University of Maryland at College Park, and Dr. Antonio Busalacci, Professor and Director of the Earth Systems Science Interdisciplinary Center, University of Maryland as well. And I am proud to say you're great Marylanders and you come from great Maryland institutions, and welcome to today's panel. Thank you.
Thank you, Mrs. Edwards. I now recognize the chair of the Environment Subcommittee, the gentleman from Oklahoma, Mr. Bridenstine, for an opening statement.
Well, thank you, Chairman Babin, and thank you for hosting this hearing today. I'm very excited about the panel that's here. I'm very excited about the prospects before our country. In so many cases, what is happening in space today is what's happening in space. It is outpacing, the commercial sector is outpacing what the government has been able to do. And that's very exciting for us to figure out how do we take advantage of what commercial industry is doing. I sit on the Armed Services Committee as well. We've been dealing a lot with the space-based communication architecture. Commercial industry has been providing massive amounts of capacity for our warfighters all over the world. And of course, they've been doing it because we had a need and commercial industry was there to meet that need. They didn't launch satellites because the government asked them to. They launched satellites to make a profit and provide a return for their shareholders. At the end of the day, The Department of Defense said we need that capability. And what's happening now, because of commercial industry, we're getting higher throughput and more capacity than we've ever seen before for our space-based communication architecture. A lot of it provided by commercial that we as a government can take advantage of. So that's an important, I think, analogy to what we're going to talk about today. I would also say that on the NOAA side, we have private companies that are preparing to launch satellites that can do things like GPS radio occultation and hyperspectral sensing. And of course, I read, Dr. Pace, I read your testimony, and you talked about how these technologies, we've been considering commercializing these technologies for a very long time, going back to the 90s, which I did not know before reading your testimony. But now commercial industry is at a point where we as a government can take advantage of these technologies in ways where we haven't before and improve our ability to predict and forecast weather, which is, of course, very important to my district. I come from the 1st District of Oklahoma. This year I've already lost one constituent to a tornado.
Expanded their offerings. Technology is also rapidly changing. For certain types of missions, solutions can be built that are much smaller in size, much lower in weight, require much less power, and offer even greater data collection capabilities. It costs much, much lower than the current systems. U.S. law and national policy directs NASA to advance the commercial space sector. Pursuant to the National Aeronautics and Space Act, NASA shall seek and encourage to the maximum extent possible the fullest commercial use of space. NASA is also directed to the extent possible and while satisfying the scientific or educational requirements of the administration and where appropriate of other federal agencies and scientific researchers, acquire where cost-effective space-based and airborne Earth remote sensing data, services, distribution, and applications from a commercial provider. A principle of the administration's United States national space policy is that the United States is committed to encouraging and facilitating the growth of a U.S. commercial space sector that supports U.S. needs, is globally competitive, and advances U.S. leadership in the generation of new markets and innovation-driven entrepreneurship. Both the 2014 National Plan for Civil Earth Observations and the 2015 National Space Weather Action Plan, as proposed by the administration, direct federal agencies to identify and pursue commercial solutions. Given the great potential for public-private partnerships, NASA is unfortunately doing very little. NASA's Earth observation program is the largest U.S. government civil remote sensing effort and perhaps the largest civil remote sensing effort in the world. NASA currently operates 26 Earth observation satellites with 12 under development. However, none of NASA's Earth observation satellites, either in operation or under development, are public-private partnerships. NASA does have a program in place to procure commercial satellite Earth observation data under the 1998 Science Data Buy Program. But the program has not been used by NASA for over a decade. It is time for NASA to initiate constructive dialogue with the private sector to assess the viability of public-private partnerships for the provision of space-based Earth observation data to meet NASA program requirements. Our nation cannot afford to simply ignore the great potential of public-private partnerships to lower costs and improve the quality of Earth observation data. There are many important issues to be discussed at today's hearing, and I look forward to hearing the testimony of our distinguished witnesses. I now recognize the ranking member, the gentlewoman from Maryland, for an opening statement.
Thank you very much, and good morning and welcome to our distinguished panel of experts. I want to start by thanking Chairman Babin and Bridenstine for calling this hearing on exploring commercial opportunities to maximize Earth science investments. I also want to thank in advance our ranking member on the Environment Subcommittee, Ms. Bonamici, for sitting in the chair when I slip away in just a few minutes, so I appreciate that. Earth observations support a myriad of applications to meet critical national needs, whether they be related to national security, weather forecasting, agriculture production, land use management, energy production, or protecting human health. Earth observations also support the scientific research and modeling that we hope can someday provide us with a comprehensive understanding of the Earth and its response to natural and human-induced changes. The collection of Earth observation data has been enabled by sustained federal investments, investments that I hope we will continue to sustain even in the midst of budgetary constraints. Those investments have enabled the development of a robust value-added industry dedicated to turning Earth observation data into usable information that can benefit broad sectors of our economy. Then, too, federal investments in the underlying Earth observations technologies and systems have resulted in capabilities that have enabled a growing commercial remote sensing industry to emerge. So it makes sense to continuously look for new ways in which we can improve our ability to carry out Earth observations and maximize our Earth science investments. Today, we'll explore the extent to which NASA might be able to leverage potential public-private partnerships to carry out its Earth science research and support the applied uses of that research. Truth be told, NASA has always had prior experience in purchasing commercial Earth observation data, and indeed makes great use of the private sector. That was my personal experience, having started out at Goddard Space Flight Center working on Landsat, but not working for NASA, but working for one of its contractors, Lockheed. And so we've made great use of the private sector and its innovation and creativity over many years. This is nothing new. In fact, in the late 1990s and early 2000s, NASA initiated public-private partnerships for Earth science research, including one for collecting ocean color data called WIFS. I don't know what that, WIYFS. The results from those early projects demonstrated potential opportunities as well as challenges associated with such partnerships. The complexities associated with such arrangements were noted in a number of studies by the National Academies of Science. For example, at least one of those studies noted that the intersection of scientific and commercial interest in public-private partnerships can pose significant challenges in attempting to meet the disparate requirements of stakeholders. This is because scientists value the free and open exchange of scientific data, the precise calibration, validation, and verification of satellite data to ensure accuracy, and long-term stewardship of data for future use and future research. However, that may not always be consistent with a company's business goals and models. In addition, it's clear that intellectual property issues related to licensing will need to be addressed, as well as issues related to data management, data continuity, and calibration if effective partnerships are to be sustained. So today, I'm looking forward to hearing whether, in light of the potential new commercial capabilities in Earth observation, there are productive ways that commercial systems can complement NASA's Earth observation data collection through the use of public-private partnerships. And if so, what mechanisms should NASA use to determine the circumstances under which public-private partnerships can effectively support the agency's Earth science research and applications, and how should those partnerships be evaluated? How can Congress ensure that the potential public-private partnerships do not inadvertently restrict and constrain research in an effort to generate revenue for the companies? And are enacted policies and authorities that enable the advent of commercial remote sensing adequate to address the future needs of both the federal government and the growing commercial remote sensing industry? Well, it's clear that there are many issues that need to be addressed.
The subcommittees on space and environment will come to order. Without objection, the chair is authorized to declare recesses of the subcommittee at any time. And welcome to today's hearing entitled Exploring Commercial Opportunities to Maximize Earth Science Investments. I recognize myself for 5 minutes for an opening statement. Good morning. I would like to welcome everyone to our hearing today, and I want to thank our witnesses for taking the time to appear before our committee. Today's hearing will explore opportunities for NASA to acquire Earth observation data through public-private partnerships, including commercial capabilities. NASA's Earth Science is the largest and fastest growing of all Science Mission Directorate programs. In the last 8 years, the Earth Science Division funding has increased by more than 63%. One reason for these budgetary increases is that NASA's Earth Science portfolio has expanded to include new responsibilities for the continuation of measurements that were formerly assigned to other agencies, including data continuity and application-focused satellite observation programs. For example, the President's fiscal year 16 budget request redefines NASA and NOAA Earth-observing satellite responsibilities. Under the new framework, NOAA is responsible only for satellite missions that contribute directly to NOAA's ability to issue weather and space weather forecasts, while NASA is responsible for all other non-defense Earth-observing satellite missions. The near-term impact of this revised framework includes the transfer of responsibility for TSIS-1, the Total and Spectral Solar Irradiance Sensor, Ozone Mapping and Profile Suite, OMPS, and JPSS-2 Radiation Budget Instrument, or RBI, and future ocean altimetry missions to NASA. Another example of increased NASA responsibilities is the Sustainable Land Imaging, or SLI, program. In the past, both USGS and NOAA have been responsible for development and operation of Landsat satellites. But now, NASA is responsible for 3 mission and development activities, including initiation of Landsat 9, along with a 4th activity to design and build a full capability Landsat 10 satellite. Given our constrained budget environment and NASA's new responsibilities, public-private partnerships may offer an opportunity to lower costs and improve Earth observation data while fulfilling science community requirements, including data continuity. Over the past decade, the United States private space-based remote sensing sector has made significant improvements in technology, products, and services. Leveraging commercial off-the-shelf technology, borrowing ideas from the information technology community, and developing innovative low-cost solutions with high-performance outcomes, the private sector is demonstrating new capabilities that could be used to address many of NASA's Earth observation data needs. In the past, Earth observations were associated almost exclusively with government-managed or government-sponsored projects. Today, commercial sources of Earth information are rapidly increasing in availability and scope. Commercial satellite systems are now reliable sources of high-resolution Earth imagery, and commercial remote sensing companies have greatly...
NATO. I've lost constituents in previous years, and I will lose constituents again next year. So taking advantage of these capabilities that have been advanced by the private sector in many ways is critically important to us as a government. I read your testimony, Mr. Shingler, about some of the ways that NASA is already partnering with the private sector. You talked about satellites as a service, and you talked about venture class launch services through the Launch Services Program, ways that we can get things into space more effectively and more cost effective so that we can take advantage of the great things that are happening in commercial industry today. And of course, remote sensing, when you talk about the National Geospatial Intelligence Agency, they're taking advantage of the capabilities of the people that are sitting on this panel right now. And they're doing it because they know that the direction you are going, you're going much more rapidly than they can go themselves. And to understand that, the idea that we can get higher resolution imagery that can provide mensurated coordinates, the idea that we can have more rapid revisit times and even motion pictures, these are capabilities now that the commercial sector is providing that we as a government absolutely must figure out how to take advantage of. Your capabilities are impressive. We need to learn what you're able to do. We need to figure out as a country, as we go forward, there is a lot of talk about what is a global public good, what is a public good. There's a lot of talk about if it is a public good, how do you as a private company protect your proprietary data that you rely on to actually provide a return on investment? These are challenging issues that this panel and other panels are going to have to work through. I want to be really clear when it comes to the Earth Sciences Division at NASA, the Science Mission Directorate. This is an agency that has been very effective in doing important work on behalf of my constituents. They are teaching us more about the Earth so that we can protect our constituents from weather, and of course the things that they have done have done just that. So Chairman Babin, thank you for having this hearing, and to our panelists, thank you for being here. I'm very much looking forward to this testimony.
Thank you, Chairman Bridenstine. Appreciate that. I now recognize the ranking member of the Subcommittee on Environment, the gentlewoman from Oregon, Ms. Bonamici, for an opening statement.
Thank you very much, Mr. Chairman, and thank you to all of our witnesses for being here today. Chairman Bridenstine and I have held a number of thoughtful and engaging hearings examining how NOAA can advance the role of the commercial sector in providing critical weather data to our national weather enterprise. We've discussed potential challenges and opportunities with numerous representatives of the weather community and with Vice Admiral Manson Brown, the Assistant Secretary of Commerce for Environmental Observation and Prediction. The message has been consistent. There are great opportunities to engage the commercial sector in ways to supplement NOAA's observational mission, but we must maintain the core policies, namely free and open access to data, that have allowed our scientific community and the American weather industry to drive innovation and economic growth. Our critical weather data must remain reliable and of the highest quality to protect the lives and livelihoods of millions around the world. In September, NOAA released its draft commercial space policy, which outlines the policies and guidelines for how the agency will engage with the commercial sector. Most importantly, NOAA reaffirms its commitment to adhere to the policy and practice of full, open, and free data exchange as established